mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
All right, grade 11s, welcome to grade 11 physics. Today is, in fact, Wednesday, May the 13th, and I'm doing this video in the afternoon, and I'm going to post it as soon as I'm done recording it. I'm going to go over the questions 18 to 21 from page 416 of your textbook. Tomorrow, if there are questions on the assignment that you're actually doing today, the handout that's on Connect, if you have those questions, ask me and I can do a video tomorrow answering those questions. But here is how we do the questions from yesterday's assignment, which was from your textbook, page 416, 18 to 21. So question 18, let's start there. And I've already done them on the board, and I'm going to walk through them with you, and hopefully they make sense this way. So in question 18, it says a 440 hertz tuning fork is held above a closed pipe. Find the spacing between resonances when the air temperature is 20 degrees Celsius. Now what you have to remember is that in a closed pipe, the first resonant will happen at a quarter of the wavelength. But then every resonant spacing after that, okay, the spacing between resonances will be 1/2 of a wavelength. And that doesn't change. The 1/2 wavelength doesn't change whether it's a closed pipe or an open pipe. The starting point is the only thing that differs between closed and open. So when we're doing this question, we're going to say, okay, we got 440 hertz. We have a velocity of 343 meters per second. That's the velocity of sound at 20 degrees Celsius. Okay, again, we can calculate that, or there's a chart in your textbook a few pages before this assignment. We had a chart of some variety of speeds of sound and various temperatures. So we're going to find the wavelength. The wavelength then is velocity over frequency, and we get 0.78 meters. Now that's the wavelength, okay? 1/2 of that wavelength will be the spacing between resonances. And so 1/2 of that number, of course, is 3.9, which is the answer that is on the page. It's page 331 out of the Solutions Manual, which you can find on the Welcome page of the Physics page in Connect. All right, so 1/2 of this is what we need to take yet. So we'll take this, we'll divide it by 2, giving us 0.39 meters as our answer. All right, there we go. Question 19, same 440 hertz tuning fork is now used with a resonating column to determine the velocity of sound in helium gas. If the spacings between resonances are 110 centimeters, what's the velocity of sound in helium? So again, you have to remember, the spacing between resonances is always 1/2 the wavelength. So when we set this up, if we have 110 centimeters as the spacing equaling to 1/2 the wavelength, that means our wavelength is 220 centimeters, or 2.2 meters. Frequency is 440. Our formula, velocity equals frequency times wavelength. 440 times 2.2, 970 meters per second. Okay, again, these are rounded to significant digits, so it may not be exactly 970. Okay, all right, I was going to slip over to the other board and we will do question 20 and 21 over there. All right, so question 20 tells us that we have a frequency of a tuning fork that is unknown. We don't know this one, but we have an air column at 27 degrees Celsius, and we find that the resonances are spaced by 20.2 centimeters. What is the frequency of the tuning fork? Use the speed of sound calculated in the example problem on the page right above the questions for the speed of sound. All right, so if 20.2 is the spacing between resonances, we know that that has to equal 1/2 the wavelength. Seeing a theme between the three questions, okay, spacing, 1/2 the wavelength. So that means our wavelength is 440 centimeters, or 0.404 meters. Velocity is 347 meters per second. Again, that's in the example problem, right above the questions that you're assigned. And frequency is 347 divided by 0.404, giving us an 859 hertz frequency. Question 21, last question. So, question 21 is a little bit more, well, it's actually not that much more difficult, but it says we have a bugle, and any bugle, trumpet, trombone, etc., is an open pipe. It's an open column, and when we straighten it out, the column length is 2.65 meters long. And it says if the speed of sound is 343, find the lowest frequency that is resonant for a bugle. So in other words, find the first resonance. Okay, so first resonance, again, always in an open column of air, happens at 1/2 the wavelength. If this was a closed column, it would be 1/4 of the wavelength, but it's 1/2 the wavelength. So again, if I draw this out, here's our open column. We've got our opening at the top and at the bottom. It's 2.65 meters long, and that has to equal 1/2 the wavelength. That means the wavelength is 5.3, right? If 2.65 is 1/2, 5.3 is the wavelength. Velocity was 343. Frequency, velocity divided by wavelength, we get a frequency of 64.7. Okay? Now when you go to part B, the only thing that changes is the wavelength. Okay? Now, so you think, well, why is the wavelength changing? It's the same size of tube. Well, that's exactly it. We have the same size of tube, but now we want to find the second and third resonances. So if we draw this one out, so here's our second resonance. Okay, we got again an opening at the top and an opening at the bottom. It's still 2.65 meters long, but now the second resonance happens at the wavelength. So now our wavelength is 2.65 meters. So when I do my frequency formula, this 5.3 changes to 2.65, and we get the answer of 129 hertz. When we move to the third resonance, again, now I've drawn it out here, okay? Again, opening top and bottom, 2.65 meters, but the third resonance happens at 1.5 of the wavelength. Okay, so this gives us again a new wavelength. We'll put that new wavelength into here instead of the 5.3, and that will give us the answer of 194 hertz. All right. Again, we can change the wavelengths by changing the frequency of the sound that we're creating. Okay, again, with a bugle, you're pursing your lips a little bit differently. If it's a trumpet, you're pressing the valve, opening and closing the valves. Trombone, you're pushing, opening and closing the slide, and making things different. All right. So, in this case, though, in a bugle, the length stays the same, but the wavelength changes in order to change the frequency. All right, I hope that answers your questions. If not, you can send me another email and we can try to find another way to explain it. But the biggest thing to remember in all these 4 questions is that there's 2 things. A, in a closed column, the first resonance happens at 1/4 of the wavelength, and then the subsequent resonances happen 1/2 wavelength apart. In an open column, the first resonance happens at 1/2 the wavelength, and then again, subsequent resonances happen at 1/2 wavelength increments. All right, so it's always 1/2 wavelength between resonances, whether it's closed or open. All right, hope that makes sense. If not, email me your questions. Tomorrow you're going to get another assignment on a handout, a bit of a review assignment, and we will keep going. And again, tomorrow morning, if there were questions on the handout you're doing today, I'll answer those questions in a video tomorrow. Have a great day. See ya.